It's probably fine. There we go. And there we go. Everybody got their phones ready? Okay, so basically we're going to finish off lecture 4 today. Hopefully we get through it all. And there'll be an assignment that is due on Friday, I believe, right? And then on Wednesday, I'll assign another assignment that we'll do. Today is Wednesday. Today, I will assign another assignment that won't be due until next Monday. Okay. So we're just all kinds of screwed up right now because the holiday and I really want to make sure you guys get this stuff covered because I promise you we don't get this. You don't know this like the back of your hand, which I don't really know the back of my hand that well, but if you don't know the back like the back of your hand, you're not going to be able to do this stuff when you get to organic one. So super important, super important. So let's go ahead and review real quick what we talked about last week. Just the last slide we had last week was this slide right here. Um, and so remember that when we're looking at these orbitals right here, these are literally atomic orbitals that correspond to the different electron configurations, right, on the periodic table. The thing I want you to notice though is, for example, we have hydrogen here, and it's one s orbital with one electron, just like it does up there on the periodic table, right? But interestingly, right, if you put two hydrogens together, right, they both have one s orbitals that can come together, right, to make a bond, and then fill up a bond so that you have two electrons now in a sigma bond, right? So that's why we know that hydrogen then can only form one bond, right? Helium is already a natural gas, a noble gas, so it can't form. It can, but normally it doesn't form any bonds with anything else. So why is it then that nitrogen, sorry, not nitrogen, carbon, I was talking about last week, carbon can actually form four bonds, right? Kind of like nitrogen can form three bonds because it has three, electrons there that still need somebody. This electron's still lonely right here. This one's still lonely, and this one's still lonely. So it still needs electrons, so it can be paired up. Oxygen only has two bonds it can form. Why is that? Because it has one bonding electron there that still needs a friend, and this one here still needs a friend too. Same thing with fluorine. To complete its octet, it still needs one friend here for this lone little electron right there, right? But then you look at carbon. I told you guys last week though that carbon um, has four bonds. It can form four bonds, right? But here you only have that's weird. You only have two non-bonding electrons right here. So it looks like from this electron configuration and these atomic orbitals that carbon can only form two bonds. Where are the rest of how can it form four bonds? And then boron too. Boron's number 3 right there. It should be able to form three bonds as well. How come? I don't understand what's going on here, right? Well, put a pin in that for just a second, right? I just want you to just remember that both boron and carbon here, right? They should be able to form three bonds and four bonds respectively, but based on their electron configuration in these atomic orbitals, carbon can only form two bonds and boron can only form one. Put a pin in that. Think about that for a second, okay? If you can come up with the reason why they can do that, please let me know, but it's a very interesting tale. So this is where we're going today. This is the exact slide that we left off on, or I got to on Monday. Was it Monday? Wednesday last week. So the theory that we like to talk about the most common theory here is called valence bond theory. And in valence bond theory, when atomic orbitals overlap, right, they actually form uh, bonds, right? So you have two types of what we call interference. Okay, we have constructive interference and we have destructive interference. And when two bonds are the same phase, right, like the same plus sign or the same minus sign, right, and they come together, right, they actually form a bond, and that's called constructive interference. It makes sense too because these two waves here, and just to review from last time, electrons can be a particle or a wave, right? And so we're treating them like a wave here. When these two electron waves come together, right? they can form a bond, and this is called constructive interference. And that, what? Yes. And you can see how these two waves, when they combine with each other in constructive interference, it's twice as big now, right? But on the other hand, if you have an electron that's in one phase, positive, let's say, and an electron that's in the negative phase over here, and you bring them close to each other, right? What do you get? You actually have destructive interference, right? There's not a big bump. There's a node there made now, right? So if you remember back when we were looking at those electron orbitals, or sorry, those atomic orbitals before, we were talking about nodes where there's no electron density at all, and then inside the actual bubbles, the orbitals is where we think that 90 to 95% of the electrons actually exist, right? This node here represents that little spot where there's no orbital at all, right? In the dumbbell, in the center, for example, right? And so the important thing to note here is that only constructive interference results in a bond, right? Because a bond has constructive interference, literally, right? You can put two of these together and you can make a bigger wave. You put them, you put different phase electrons together, and then you get destructive interference and you form a node. Okay, so this is your first question. Go ahead and try this out. Make sure you're on the Wi-Fi. Make sure you're on the Wi-Fi. And oh, I signed in. So we can see. Anybody having any problems? Oh my gosh. There are some Wi-Fi issues recently. That's why I was asking if you were having problems on the Wi-Fi. And it could have just been me. Oh my God. Enter a code. Why do I always have to enter a code? I log into this thing every week. 833-717. Oh, don't tell anybody I said that. You don't want to know my secret code. What the heck is happening here? Why is the code not working? Don't ask again for the rest of the freaking month. It's killing me is what it is. Okay, let's see how everybody answered. Let's see here. Interference. I believe that's the question. Yes, that's it. We've got 11 people in here? Oh, yeah, because Daniel's not here. That's right. All right. Well, good job. Good job. It is definitely constructive interference, which is the reason why we can form bonds, right? Destructive interference only forms nodes. Remember that, okay? So a lot of the easier questions that are going to be on the exam, like the multiple choice questions, are going to be things like, which can form, which kind of interference forms a bond, which kind of interference forms a thing, about, all the above, or none of the above. So I'll try to trick you with those kinds of things, so don't fall for it, okay? With the all of the aboves and none of the aboves. Okay. So let's take a quick look at, switch over back. So let's take a look at valence bond theory then, right? And as I alluded to before, oh, I can't go that far. Damn it. As I alluded to before, right? Remember that a s orbital, right? We had the hydrogen atom. All it had was one s electron in an s orbital, right? And it was circular shaped. Remember that from last week, right? Not p shaped. The p orbitals are the ones that look like dumbbells. S orbitals look like balls, right? And so two hydrogen atoms can come together, right? And when they're two orbitals, they're two of them, right? Of the one s orbitals come together, right? You get this direct overlap that forms, and then what you get then as a result is what we call a sigma bond. Okay, it's called a sigma bond. And so those bonded electrons spend most of their time in the overlapping space, right? And that's why these two atoms are now sharing their electrons, right? In this little sigma bond here. So that's another thing you need to remember. S orbitals come together to make what? Sigma bonds, right? They come together to make sigma bonds. Um, so if you remember from last week, which is a long time ago, I know, we were talking about that graph where as two nuclei come closer and closer and closer to each other, right, they start to interact with each other, right? And then when the attractive forces overcome the repelling forces, remember what the repelling forces were? Anybody remember? Electron forces are repelling, right? Nuclear forces are also repelling. What are the attractive forces? It was a nuclear electron, right? Nuclear electron. So when those attractive forces happen and they overcome the repelling forces between the electrons and between the nuclei of each atom, right? Then that's when you start to form this overlap with the orbitals, and then they're very much happy together because they're at a very low energy, right? They're at a very low energy. What happens when they get too close to each other? Then they just repel each other and bounce off, right? Or explode, right? That's like when you see, um, do you know what the CERN super collider is? The CERN super collider is this thing in Switzerland, or maybe it's in Sweden. And what they literally do there is they have like atoms and they just throw them at each other to make new atoms, right? Like, and it's a huge like circular thing, right? Like huge. It's like the size of this building, and they make the atoms go around in a circle, and they just fly around in the circle, like just for a long time. I don't know how long, and then they'll just insert another atom in there and make them collide, and they'll either repel each other or they make a new atom. In fact, most of the atoms down here, the elements down here, were all made that way. They were made by colliding nuclei together, right, to make new atoms. Anyway, that's a aside from the fact that if the two nuclei are so far apart, they don't interact with each other at all. When they come close to each other at that right perfect moment when the energy is low enough and they overcome the repulsive forces, they become a compound. Like here, it's hydrogen gas, right? But if it gets too close to each other, they'll just repel each other some more, right? And the energy is too high and they won't want to be together anymore, right? So let's put all that together now and introduce then, we were just talking about valence bond theory. The most important bond theory, though, is called the molecular orbital theory, right? And what I want you to notice about the molecular orbital theory is that notice here, we have the one s electron from hydrogen, one hydrogen atom, and another one s electron here from another hydrogen atom, right? So that's two 1s electrons, okay? When they come together, when those two hydrogen atoms come together, right? And they've come together right here, right? They come together right there. They form a bonding molecular orbital, right? It makes sense. It's pretty self-explanatory, right? It makes sense. It makes a bonding molecular orbital. And you can see in there, it's kind of hard to see, but you see two atoms of hydrogen together right there, right? Making hydrogen gas. But the other thing you see too is at the top. And this is called the anti-bonding molecular orbital, right? And notice that there's a node right here, right? There's a node right there. Very similar to the node that you see during valence bond theory when you had those two waves that were different phases, right? And what do? You get a node, right? And no bond being formed. So notice up here, you get two phases, and what's not there? Sharing electrons, right? Where would those electrons rather be? Down here, because it's lower energy, right? Not to mention the fact that when you have a sphere with two electrons in it, and those electrons are bouncing back and forth with each other inside the electrons, there's more room to breathe. There's more room to move around. So it's less energy. But then you go up to the anti-bonding molecular orbital, which has two different phases. You split it with a node, right? You split it with a node. Now you have half the area for the electrons to exist in, right? So where would the electrons rather be? They'd rather be in the bonding molecular orbital, right? And notice that the bonding molecular orbital here is lower energy than the 1s orbitals. But that makes sense. It has to be lower energy, right? Why would they even want to bond if they weren't lower energy to begin with? The point of all this, right, of molecules coming together or atoms coming together to make molecules is so that they can achieve a lower energy. If they're not going to achieve a lower energy, then they're not going to want to do it, right? They're not going to want to be a pair with somebody else. Okay. So this, I cannot stress this enough. This is so important right here. Okay. When you have two atomic orbitals and you put them together to make molecular orbitals, there will always be two molecular orbitals too, right? So here's two 1s orbitals. They came together, and now you have one bonding molecular orbital and one anti-bonding molecular orbital. You see that? So there's two molecular orbitals, there's two atomic orbitals. They will always be equal in number, okay? Forever, however many atomic orbitals you have, you'll always end up with the same what? Number of molecular orbitals. Does that make sense? Okay. Oh, look, I didn't even realize I said this. See, constructive and destructive interference. See, I'm glad I wrote that in there so that when you look back at these notes, you remember that that goes back to the valence bond theory when we had the waves, right? It's good stuff. It's good stuff. So, taking a closer look at this here, which I'm probably just going to repeat myself because I said everything on the previous slide. I usually do that, right? The anti-bonding molecular orbital has a higher energy because it has one node in it, right? But so when the atomic orbitals overlap, the electrons go to the bonding molecular orbital rather than the anti-bonding in order to achieve a lower energy state. So literally, this slide just says exactly what I said in the last slide, right? But just written out for you. Okay. Does that make sense, everybody? So how many molecular orbitals am I going to have if I put together two atomic orbitals? Two, exactly. And that's just for the hydrogen atom, right? I mean, look how many elements you can put together. You just need to remember, right? Whenever it's always going to be the same number of atomic orbitals, the molecular orbitals are. Okay? Good stuff, good stuff. So let's take a look at this molecule, right? This is methyl bromide. Methyl bromide, it's a carbon with three hydrogens on it, and it's connected to a bromide, right? Or a bromine, okay? There are more than two molecular orbitals that exist, right? But we'll only focus on two of them here, right? The thing that I want you to notice is that those molecular orbitals actually expand, bless you, they actually not expand, they span, right? Expand makes it sound like they're getting bigger. They're not getting bigger. They just span the entire length of the molecule, right? And what that means is that when you span the entire length of the molecule with the molecular orbital, that means the electrons can be shared throughout the molecule. Does that make sense? They're just bouncing around all happy inside, okay? Right? So there are many areas of atomic overlap and nodes as well. So notice how the MOs extend over the entire molecule, okay? So there's a couple of different things to notice here, right? There's these two terms. One is HOMO and the other is LUMO. HOMO stands for the highest occupied molecular orbital, right? So which molecular orbital, that's the ones that are in the center, is the highest occupied one. And then the other one is LUMO, which stands for the lowest unoccupied molecular orbital, okay? And we care about these things because when electrons get excited, for example, right, it's the ones that are in the highest orbital that get excited to the one that is lowest that's unoccupied, right? And then when they come back down, you get things like light or colors or any kind of like reflection of color or light or anything like that, any kind of release of energy, okay? So let's use hydrogen as our example because it's pretty easy, right? What's the highest molecular orbital? It's this one right here, right? The highest occupied molecular orbital, it's that one right there. And what's the lowest unoccupied molecular orbital? It's that one right there, right? Because there's only two there, right? But when you get a bigger molecule, there'll be a lot more to deal with. Okay, so here is your next question. And I promise you, we'll get back to why carbon has 4 bonds in a second, even though it only has 2 valence electrons. That's just nuts, right? Like, is all chemistry wrong when I'm telling you that carbon has 4 bonds and and you can form four bonds with carbon, but it only has two open valence electrons that need to be paired. It's just crazy. It's absolutely crazy. And I tell you, when I found out about it, why it was, I was just like mind blown, right? I promise you'll care more about it later too, later in life. When I was learning about it when I was in Gen Chem, I really didn't care, and I'm sure I was told about it when I was in Gen Chem. But then when I was a grad student, I learned it again. And I was like, holy crap, is that for real? I had no idea. And they'd say to me, my prof would be like, I told you this in like Gen Chem 1. I'm like, oh, maybe I should have paid attention in Gen Chem 1. Oh, man. Okay, so this is number of AOs. Let's see here. There it is. 8 responses so far. And you guys are killing me here because you guys are getting all the answers right. When you get all the answers right, I can't make you talk about it in your groups. So thanks a lot for that. But good job getting it right. I expect everyone to get that answer correct on the homework assignment, okay? All right. So are we missing? Oh, there's 11. Okay. There we go. That's good. So let's not talk about then carbon. What's going on here? Like, what is going on with carbon? Okay. So if you take a look at carbon, right? This is carbon right here. Inside, no. I forgot to change it back to drawing. So this is carbon here, right? Inside of inside of 4 hydrogens, and it's actually the methane molecule, right? It's the molecule methane. It's the same thing that we use in our stoves, gas stoves. It's flowing through. Fun fact, I don't know if you knew this, but methane actually doesn't have a smell. So whenever you have a gas leak and you smell something, it's huh? No, actually, propane doesn't have a smell either, right? And it actually, a funny thing, I didn't know this until recently, because of the freeze, the deep freeze we had in February, right? Turns out that the methane gas is actually laced with hydrogen sulfide, and it's sulfur that you smell exactly when you have a leak.
Okay, so we have these like huge heaters on our back porch at my parents' house.
Yeah.
And like the ones that they're metal and stuff.
Yeah.
Okay, well, the heater was on.
Yeah.
Which like this was like really a coincidence. It did not blow up.
Yeah.
The heater was on, so obviously the propane or the gas and stuff, you have to twist it so
Yeah.
it goes through the thing. Well, one of my friends was over there and he was smoking a cigarette, and he thought that he could obviously see that the heater, like, the bottom of it was not a trash can. He throws his lit cigarette
No way.
inside of it.
Oh my God.
And I like looked at him and I said, "Did you just throw that in there?" And he was like, "Yeah, it's a trash can, right?" I like ran over and I was like, "Oh God, let me turn off the gas." Like,
Luckily, you didn't have a leak.
Was like, wow. But whenever you unscrew the tank,
yeah,
to get like the heat through it,
yeah,
you can still smell it.
It's a pretty strong smell.
Yeah. Like, so how would you know if you necessarily have a leak?
It'd be a lot stronger. Yeah.
Okay.
Like, so the reason why you use hydrogen sulfide is because our noses are actually very sensitive to sulfur compounds. Like, quite literally, like the smell that's in flatulence is actually sulfur gases that are made from bacteria in your body, right? So most people think it's like methane, like whenever you watch South Park and Cartman is like lighting Kenny's, farts on fire type of thing, right? That actually is methane. It could happen. But it's not actually what smells. What smells is the sulfur compounds that are being made by your bacteria inside your gut.
Because methane is in our gas, right?
Yes. Like the stuff that's going through your natural gas underground is all methane.
Yeah, yes. But even like us human bodies.
Yes, that is absolutely true too.
Like,
yes.
Same with like plants and stuff like.
Yes. That's how the bacteria metabolize their nutrients, right? They actually their waste product is gas, quite literally, right? And so that's also like why like cows, right? They have
Oh yeah, they have very high methane, don't
exactly
they?
because
Yes,
they
that's
have
what I was thinking of.
yeah because they have ruminant stomachs that have like I think four of them or something like that,
Yeah,
and each one has like special bacteria in it that break down plants. That's why cows can eat
yeah.
grass, and the way they after they've done breaking it down, their waste product quite literally is methane gas. So there's like research projects in the works right now to literally harvest the methane coming from cows to pipe it through our natural gas because we're running out of natural gas.
What do you do with like?
It's quite
Do you
crazy.
just like I don't? Okay,
Yeah.
anyways.
So so fun fact there, you don't actually smell methane when you're smelling your gas leak. You're actually smelling sulfur compounds. Quite literally, it smells like dying fish, like nasty, nasty dying fish. So um, yeah, so if you didn't know that, that's pretty cool, right? So that's the methane molecule right there. And methane, as you can see, like I said before, has four bonds to it, to that carbon right there, right? And that four bonds means it's tetravalent because tetra is four in Greek. So what if you're nitrogen? What are you? You're trivalent, right? Because trivalent is three in Greek, right? Hydrogen is monovalent because it's only got one bond, right? One is mono in Greek. And then uh, not carbon, sorry, oxygen is divalent because di means two in Greek, right? So when I say that a molecule, or sorry, not a molecule, when I say an atom like fluorine is monovalent, what does that mean? It means it can form one bond, right? So here you can see that the hydrogen has formed, four hydrogens have formed bonds around this carbon here. So carbon here is tetravalent, right? But the other interesting thing about carbon being tetravalent is that where those hydrogens are, this is called a tetrahedral, and they are in equal distance from each other as far as the bond angle goes, right? The angle from here to here is 109.5 degrees. The angle from here to here is 109.5 degrees. The angle from here to here is 109.5 degrees. So what that suggests then is that since they are all equal distance from each other, they are all bonding to the carbon in the same energy, right? They're all equal energy, each one of those bonds. So let's take a look at this here, right? Let's take a look at carbon's atomic orbitals, right? Uh, and this is what we saw before, actually, right? This is what we saw before, where we have one electron here that needs to be paired. It's lonely. We have one electron here that needs to be paired. It's lonely. But the other two are already paired, right? So how do we get from this divalent configuration, right, to a tetravalent carbon? Well, this guy, our friend and yours, I think his name was Linus Pauling, right, came up with this theory, right, where atomic orbitals can get hybridized. And so instead of having this electron pair down here, it actually gets excited. And now it goes to the 2p orbital, right? It goes to one of those 2p orbitals. Just for giggles, let's just call it X, Y, and Z, right? And so this electron here that's in the 2s orbital gets promoted to the 2pz orbital. And so now, when it's all said and done, now how many electrons do you have that are free for bonding? Four of them, right? Now it's tetravalent. Does that make sense? But there's still a problem. Can anyone tell me what the problem is? Say that again. Because we know in real life, right, that carbon makes methane, right? Carbon is in methane, and it has four hydrogens around it. And when we look at methane, all these hydrogens are surrounding methane in an equal manner, right? Okay. But when you look at carbon's electron configuration, there's only two available electrons to make bonds with, right? How is that possible then? When you have methane here, it's got four bonds. It should have four free electrons to make bonds with, right? And so we're like, what's going on here, right? Well, Linus Pauling said maybe what's happening is that one of the electrons that's paired up already in the 2s orbital gets promoted, right? It gets promoted or excited to the 2pz orbital. And when that happens, what do you have now? One, two, three, four. Four free electrons to be bonded with. Does that make sense? Yeah, that's why I was saying that, right? So let me ask again then. What's wrong with this picture still? There's still something wrong with this picture. That's exactly right. That is exactly right. How can this be the new configuration, right? When in real life we see methane as a molecule that has hydrogens bonded to it, right? Equally. This electron here is lower energy. And these three are the same energy. So if anything, it should be kind of lopsided, right? But it's not. I am so proud of you guys for getting that, right? That's really important right there. Because all molecules have this problem, and you'll see it in a second, right? How do we fix this then? How do we fix the fact that this electron configuration here, though it accounts for having 4 bonds, but it doesn't account for the fact that in real life, what do we have? A methane molecule that is equally bonded to 4 hydrogens, right? Does that make sense, Mary? Okay, one more time. It doesn't make sense, right? Because in real life, we have we have a methane molecule, right? Say again? This one? No, this is all carbon right here. This is our see. Um, each thing is a free electron that's around carbon, right? Like this. Let me just draw it out for you real quick. If I had a pencil, I do have a pencil. So remember, I said that carbon is tetravalent, right? It looks like that when before it gets bonded. Okay, so this electron here is like that electron. 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 Right? Which one? This one right here? That's the inner one, right? Remember, we're talking about valence electrons. The electrons are on the outer orbital, the outer shell, right? So remember how we were going across here, the top of the periodic table, and I keep on saying, carbon has how many valence electrons? It has 4, right? But in total, how many electrons does it have? 6, because there's still 2 electrons that are in the 1s orbital, but it's inside. Those are the inner orbital, right? Remember that? Yeah.
So about it not being equal, right?
Yeah.
So like it's equal right now. That's how it looks weird like that, right? But if we fix it, will it become equal? Like, does that make sense?
I know exactly what you're saying.
Like,
I totally understand what you're saying, and I will tell you in just a second.
okay.
Let me make sure that we get this part first, right? Remember that carbon has a total of how many electrons? 6, right? Because its atomic number is 6, right? And the number of protons equals the numbers of electrons, right, in the neutral atom. So that's 6. But it has 4 valence electrons, because those are the electrons on the outside, right? And then the center, right? So there's the first shell is called the 1s orbital, right? That's why it's up here, 1s orbital. And then the second shell is called the 2s orbital. And then all 4 of carbon's electrons that are available for bonding, right, are in the 2s orbital, right? Or sorry, not 2s orbital, but the second orbital. Yes, exactly. Exactly. Does that make sense?
Yeah.
Okay. Yeah. So if you look at this, right? So someone took a methane molecule and did spectroscopy on it. They put it into an instrument and they measured the distance between the carbon and the hydrogen, right? And they measured the distance between the the 2 hydrogens, 2 of the hydrogens, right? And they did math and they figured out that each of these distances for every one of these hydrogens is the same, right? So that suggests then that they're all bonding to carbon at the same energy, right? But then when you look at the configuration here, the electron configuration, the question then is, how is that possible when one of them is lower energy than the other 3, right? Right? Because if this was the real configuration, what should it really look like? It should look like this. Like 3 of them the same, right? And one of them super long. Whoops. No, I don't need you, Siri. Not now, Siri. Right? Does that make sense?
Yeah.
Right? One of them super long instead of them all being the same distance from each other. right? Because how do you get something lower energy? You pull it away from each other, right? Does that make sense now? Yeah. Okay. Yes. This is a very important concept here because if you're going on to organic 1 and organic 2, you cannot get through without understanding what's happening here. So how do we get it so that this electron configuration then, right, matches what we see in real life? We get it by doing hybridization. Okay, hybridization. So when Linus Pauling first did this, right, all he said was one of the electrons from the 2s orbital, right, they get promoted to the 2pz orbital. So now you have 4 free. So you have your tetravalent, right? You have your tetravalent now, your tetravalent carbon, okay? But that wasn't far enough because that tetravalent carbon didn't have equal energy with all of its bonds. And so the next step in this was called hybridization, where not only does one of the electrons get promoted to the 2pz orbital, right? But then they all rearrange themselves, right? So they're somewhere in between the two, and then all 4 electrons are the same energy. That's called hybridization. Okay? Yes, ma'am.
So we get rid of the 2s
Yes.
orbital.
Yes, and we also get rid of the 2p orbital too.
So
Now it's called the sp3 orbital. Isn't that crazy? It's so crazy. Like, who would have thought of this? Not me. I'm not smart enough. But the thing I want you to notice, though, is this. You really didn't get rid of anything, right? Hannah, look at this real quick. You didn't get rid of anything because you have one s orbital here, and you have 3 p orbitals there, right? But look at the name now. One s orbital, and how many p orbitals? 3. That's why it's called an sp3 orbital, right? So every single carbon, right? Every single carbon, or even atom for that matter, that is tetrahedral and has 4 bonds is considered sp3 hybridized, right? Yes, ma'am. Doesn't matter. Doesn't matter. What happened? It depends on how many things are bonding to it. I'll tell you in a second, right? We'll get to nitrogen in a second. It depends on how many things. Go ahead, Hannah. Sorry.
So since it does turn into sp3, so we don't get rid of the 2s, but
it just goes.
When you moved up, the reason why there is an s for it, it's because we added
Yeah.
s orbital to the whole thing.
Right. We brought down the 2 p's to this level right here,
Okay.
and we brought the s's up to the middle as well. So now one of these is an s orbital, and the other 3 are what? P orbitals. But they're all the same orbital now, right? Or sorry, not the same orbital, but the same energy now, right? And so that's what we call it, and that's what the word degenerate means. Degenerate means the same energy. And now we call it the sp3 orbital because the s orbital's there, and then all 3 of the p orbitals are there too.
So why would you put 2s and 2p? So why would you put 2s, 2p3 instead of just sp3?
The reason why is because this 2s right here is corresponding to this energy, right? And these 2p up here is corresponding to this energy up here. So it changes its name, right? As you go down in the periodic table, the energy changes with the orbitals, right? So you can't use the same name here because it's a different energy, right? Everybody got that so far? That blew my mind when I first learned that. So I know it's after lunchtime. Actually, it is lunchtime. Dang, this is so cool. So cool. So let's take a closer look at the sp3 orbital then, right? Again, we see here exact same thing as before, right? We have our 3 that are 2p's, the 2py, 2px, 2py, 2pz's up there. We have the 2s right there. They hybridize, and we get the sp3 orbitals that are all the same energy, right? Don't even worry about the 1s because they're not bonding to anything, right? They're not on the outside. So why would you care about the 1s orbitals, right? The only thing you care about is the one that bonds with things. And in this case, it's the 2p orbitals and the 2s, right? And so the thing about it is that when we take a look at this bond now, right, this is what it looks like. So the shape of the sp3 orbital results from having 25% s character and 75% p character. What does that mean? It's because you have one of these, which is 25% of 4, is S, right? And the other 3 is P. And that's why it's 75%. Go ahead.
Okay, so how do we, why would it 1s? Like, how do we know that 1s isn't being bonded? Like the 1s orbital.
So the only ones that have any bonding with the 1s orbital is going to be hydrogen.
Yeah, but we are bonding with hydrogen.
I mean, sorry, let me rephrase that.
The only one with one.
Huh? What?
The only one that has one singular thing is hydrogen.
Right. Because helium is already a noble gas. It's not going to bond with anything.
Yeah.
Right? So you are bonding with hydrogen here, but you would treat hydrogen the same way you would treat like fluorine, for example, here, as just having an electron to share to get a full octet, right? So the thing about it is that you're not doing any really hybridization in hydrogen, right? Because hydrogen doesn't have enough electrons to do any hybridization, right? You've got to have at least 4 or 3 actually, right? So hydrogen is not doing any kind of hybridization because it doesn't have enough electrons.
Certainly carbon is doing it.
So I'm never going to ask you for a question like, what is the hybridization of hydrogen? It's always going to be the same, right? But I will ask you the question, what is the hybridization of carbon?
Okay, so we are hybridizing. That's carbon up there. That's not hydrogen.
Right.
Okay.
Yes.
That's my question. I was like, wait. What?
Yeah, remember, hydrogen only has 1 electron.
Yeah, that's why I was confused on why it wouldn't be in the, like, why we wouldn't bond with 1s.
Yes.
But
Yeah. No. I was just using it as an example, right? I was using it as an example here, right? Because it's such a common molecule, right? But you could just as easily put a fluorine on each of those, or put a chlorine or a bromine on each of those. In fact, my very first thing said methyl bromide, remember? It doesn't matter because all of those only have 1 electron that they're trying to share.
Yeah. So for like bonds like this,
Yeah.
right? Will we have to hybridize all of them?
Well, it depends. We'll get there in a second. I'll show you it depends. It absolutely depends. It also depends on your question too with nitrogen, right? Because anything that has more than 1 bond can do hybridization,
Okay.
right? So nitrogen can do hybridization because it has 3 bonds, right? Oxygen can do hybridization. It has 2 bonds, right? So we'll get to that in a second. Okay, because we still are not done with hybridization yet. Okay, before we move on from this, does anybody have any questions? Any questions? Okay. So take a look at this then, right? Now that we have, oh, this is a good picture to show you too, Hannah, because notice here, right, the one free electron in each,
Yeah.
right? So it's like there's no real hybridization that can occur with hydrogen itself, right? But the carbon can get hybridized. Its orbitals can get hybridized so that it can bond with hydrogen, right? So here, to make the C4H4 or the methyl, to make the methyl molecule, the 1s atomic orbitals of the 4 hydrogen atoms will overlap, right, with the sp3 hybrid orbitals of the carbon. So literally what happens here is that these 1s orbitals stay 1s, right? They stay 1s, and then they overlap with the sp3 orbitals of carbon, right? And that's how you form the bond. Carbon is getting hybridized, not hydrogen.
So technically, you would have to hybridize it before it could bond.
Hybridized carbon?
Yeah, or hybridize the whole thing. You said so they overlap and it hybridizes, right?
Well, it'd have to be hybridized first.
Oh, okay.
Yes.
And then they overlap, and then it becomes.
Yeah.
Okay.
Yeah. Well, honestly, that's a good question because no one's ever actually like observed it before, like at an atomic level. So it could be that the hydrogens are forcing the hybridization.
Yeah, because you said
So
that the carbon, the hydrogens attach themselves to the sp3
yes,
level in carbon, right?
yes.
So you said that before they like you said that part when you were talking about that one, and then you said the next part where they started overlapping. So I was just confused on like if
You're confused with
would have to be.
you're confused with the order.
No.
The order that
The
it happens.
question is, like,
It doesn't matter the order.
oh, no. Okay, so let me figure out how to word this.
Okay.
So carbon is already hybridized in that picture,
Right.
The first one.
This one right here. Yes.
Yeah. And then they overlap, and
Then
hydrogen becomes part of that.
Yes.
Level.
Yes.
Okay.
Yes. Absolutely. Yeah, because remember before over here, right? We didn't even have the hydrogen yet, right? There's no hydrogen there yet, and it's already hybridized, right? Hydrogen hasn't bonded with this yet, and it's already hybridized. Okay, so notice that after hydrogen's s orbitals hybridize, it's not hybridized, sorry, I just said that wrong. Don't write that down. Notice that when hydrogen's 1s orbitals overlap with the hybridized sp3 orbitals of carbon, right? You now get the 109 degrees, 109.5 degrees measurements all the way around the entire tetrahedral, right? That we saw in real life. If that makes any sense. Does that make sense? Okay, so I know that was crazy, right? But let's try another one here. This is another molecule, okay, called ethylene. Okay, let me actually draw it so you can actually see what it actually looks like. So ethylene looks like this. It's a carbon with two bonds, right? Double bond like that. Like that. That's ethylene. Okay. I think ethylene is the same gas that gets emitted from your fruits and vegetables. It makes them go bad, right?
Wait, what did you say? I'm sorry.
Ethylene is like the same gas that gets emitted from your fruits and vegetables that makes them go bad, that makes them, spoil or rotten or whatever. You know, like lettuce leaves will wilt, and that's because of ethylene gas, right? So that's why you're not supposed to put your vegetables into a Ziploc bag and then put them in the refrigerator, because the Ziploc bag will keep all the ethylene gas in there. It'll make your vegetables not last as long. That's why they tell you to keep it in a drawer, just open, or leave bananas or apples out in a bowl, right? So, interesting thing about ethylene, though, right? Ethylene is not sp3 hybridized, right? It's not sp3 hybridized. It's something else. So here we go. Again, we have here the same configuration as we did before with the sp3, right? Where we had the Linus Pauling thing, had the electron from the 2s orbital get promoted to this guy up here, to this 2p orbital, right? But since this is a double bond right here, this is a double bond, it turns out that you don't actually have to even worry about that p orbital electron for the hybridization, right? And so what's only going to get hybridized then is the 2s orbital and then the 2px and the 2py orbital, right? The 2pz orbital stays at the higher energy, right? It stays at the higher energy. And then the 2p, 2px and 2py orbitals hybridize with the 2s orbital, making 3 degenerate orbitals. And this is borne out because the easy way to figure out what the hybridization is of a carbon is to count the electron domains, right? So for this one, there is an electron domain right here, the bond between hydrogen and carbon. There's an electron domain up here, the bond between hydrogen and carbon. And then there's an electron domain right here between these two carbons. That's 3 electron domains, right? How many hybridized orbitals do we have? 3 hybridized orbitals, right? One of them is an s orbital. When you have hybridization, by the way, when you have hybridization, there will always be at least one s orbital, right? The thing that starts to decrease is the number of p orbitals, okay? So there's one s orbital here, and then 2 p orbitals here. They're all degenerate, right? And so we call that the sp2 orbitals, right? So this carbon right here then is sp2 hybridized, okay? Compare that to this guy right here, which is sp3 hybridized, right? Why is it sp3 hybridized? Because it has 1, 2, 3, 4, right? So 1s, 3p makes 4, right? And then when you look at methane, how many electron domains does it have? 1 between that hydrogen, 2 between that hydrogen and the carbon, 3 between that hydrogen and carbon, and 4, right? So literally the number of electron domains tells you how many, or tells you what the hybridization is. You have 4 electron domains. What do you have? sp3, right? 1s, 3 ps. Okay. You move on to a molecule like ethylene, right? A molecule like ethylene, and what do you get? You have 3 electron domains. Don't count the number of bonds. Count the areas where there are actually electrons present, right, that are sharing. And so you get 1 here, 2 electron domains there, and then 3 electron domains there. We only do this one at a time. You can hybridize this carbon later, right? You can figure out what the hybridization of this carbon later. But it's exactly the same as this one. So they're both what? They're both sp2 hybridized. If it's symmetrical, absolutely. Right? This carbon right here is symmetrical to that carbon right there, right? And so if this carbon here has 3 electron domains, so does this carbon, which makes it an sp2 hybridized orbital. Does that make sense?
So for the electron domain, it's not the number of bonds, but the areas that there are bonds.
Exactly.
Okay.
Exactly. That's why we call them electron domains and not call them count the bonds, right? Count. Absolutely. Only 3. Every single time. If there are 3 electron domains, it's sp2 hybridized. What if it's got 4 electron domains? sp3 hybridized. Exactly.
Okay.
Right? We're counting these down now. We're getting there, right? There's a pattern. There's a pattern. I promise. Okay. So, everybody good with this so far? Okay. So when you're looking at this orbital here, right? So what's actually happening then is that 2 of these orbitals, or sorry, not 2 of them, but 3 of these orbitals right here, right, are going to form 1 bond here with the hydrogen, 1 bond here with that hydrogen, and 1 of the bonds of the double bond. Okay? And then this last p orbital right here makes that second bond of the double bond. That bond is called the pi bond. Okay? It's called the pi bond. So notice how we go, s orbitals make what? Sigma bonds. P orbitals make what? Exactly. And then a double bond consists of what? 1 sigma bond and 1 pi bond. Does that make sense? It's crazy stuff, isn't it? It's absolutely crazy stuff. Yes, ma'am. Which part? All of it? Kidding. Totally kidding. No. So pi, yeah, like the number, pi 3.1415675535536, something like that.
Wow.
I only know it to like 10 digits. So anyway, and I could be wrong. It could have changed over time. Who knows, right? So let me go over this one more time because again, this is very important. Okay. All 3 of these bonds right here, right? These sp2 hybridized orbitals, they form sigma bonds. Okay. One of them here is forming a sigma bond between the carbon and the hydrogen. One of them here is forming a sigma bond between the carbon and that hydrogen. And then the last one is forming a sigma bond between the carbon and the carbon. Okay? Does that make sense? Okay? But then we have this 2p left over right here, and it's forming the pi bond between the carbon and carbon, right? And that's why we have a double bond between that carbon and carbon, right? Because a double bond consists of what? A sigma bond and a pi bond, right? You'll see later on in life that people just do the shortcut and say it's a pi bond when they see double bonds, right? But really, that's what it consists of, okay? So the key here is to know that s orbitals make what kind of bonds? Sigma bonds. P orbitals make what kind of bonds? Pi bonds, exactly. Okay, good stuff, good stuff. Man, I'm on a roll. Let's keep going. I mean, it's so exciting. Okay, all right. So just like the other slide we had for the sp3 orbital, right? If we look at the character of the bond, here in sp2, we have 1s2p, right? P2, whatever. I'm dyslexic, right? And so when you look at the character, it's 33% S character, right? And 67% P character. Really, it's 66.6666666% P character. But it makes sense, right? Because 2/3 of that hybridized carbon orbitals is what? P. And then 1/3 is what? S. And so you have 33% character for the S orbital. You have 67% character for the P orbital. Does that make sense? Right? What was it in the last one?
25%.
Exactly, 25%, 75%, right? So if you take a look at this right here, right? You see how this is that one p orbital right here, the py orbital? That's the one that's not hybridized. You can tell it's not hybridized. Why? Because it still has two different phases, right? And then the gray ones here, those are the hybridized sp2 orbitals, right? And so notice what's going to happen here. This one here will come over here and form a bond with the hydrogen. This one here will form a bond with the other hydrogen, right, in ethylene. This one here will form a bond with carbon, the sigma bond with carbon. And then this one here, this p orbital, will do what? It will form a pi bond with the other carbon, right? And something tells me I kind of jumped the gun. And I did jump the gun because that's exactly what this shows. See? I tend to explain things before the picture actually comes up. So notice, right? Here's the hydrogen that's forming a bond with the sp2 hybridized orbital of carbon here. Here's the other one here, right? The other sp2 hybridized with the hydrogen there. And then we have the one here, which is the sigma bond between these two sp2 hybridized orbitals. And then here is the pi bond up here. It hasn't drawn it out yet, but quite literally, that's what it looks like. And that's your pi bond at the top. Okay? So you see that now, right? This is still ethylene. We're still ethylene right now. And we see a sigma bond there and a pi bond there. What is this called? A double bond, right? And then we have the hydrogen bonding with the carbon here. It's a single bond, but it's also a what? Sigma bond, right? Because s orbitals do what? They make sigma bonds, right? I think the thing that people will forget, though, that you need to really remember is that a pi bond, a double bond contains one sigma bond and one pi bond. That's the thing that people need to remember. Okay, so this is again me jumping the gun here. I drew it for you in the last slide, but it's telling you here, right? The pi bond is formed by side-by-side overlap of the p orbitals, right? So here we have side-by-side overlap of the p orbitals, okay? And then you can have a pi bond there, right? You can have a pi bond there. The electron density of the pi bond is spread out above and below the plane of the molecule, right? Pi bond. So the thing that you need to remember also about pi bonds is that they're definitely weaker than sigma bonds. Okay, they're definitely weaker than sigma bonds. Anybody have any questions so far? Any questions? Okay. All right. Okay. Let's talk a little bit here about pi bonds then. Okay. About the 2p orbitals, right? So here we have a 2p orbital. Pretend it's that 2p orbital from the previous ethylene molecule, right? And here we have a 2p orbital from the other carbon, right? That didn't get hybridized. It still wants to bond too because there's still a free electron there that's lonely and it wants to have a partner, right? So it's going to share. They'll share it with each other. And when it comes together, two p orbitals come together. How many molecular orbitals do we get? Two molecular orbitals, right? Okay. And we get two molecular orbitals. Okay. We have the pi bonding molecular orbital and the pi anti-bonding molecular orbital. And it's even more apparent now that these electrons would rather be here at the pi bonding molecular orbitals than they would be in the pi anti-bonding molecular orbitals, because look how much space there is there. That's like no space at all. That's super high energy, right? And this is super low energy, right? What was this called when we had the s orbitals? This here with the p orbitals is called the pi bonding molecular orbitals, right? What was it called when we had the s orbitals with hydrogen? Yes, the sigma bonding molecular orbital. Good job. Exactly right. All right. All right. We're getting down to it now. Okay. Here's another molecule. This is called acetylene, right? This is called acetylene. And acetylene, how many electron domains do we have in acetylene? What? How many electron bond? How many electron domains? No, two, right? Because if you look at carbon, right, this is an electron domain here, and that's an electron domain, right? Remember, you're counting the areas where there are electrons for a single carbon, right? You're not counting the number of bonds. You're not counting all of the bonds or all of the areas, but you're counting the electron domains around a single carbon, okay? And the thing is the same on the other side because acetylene is what? Symmetrical, right? So this carbon has two electron domains. And how many does this one have? Two, because they're symmetrical, right? It's going to be the same, okay? Well, interestingly enough, when you have only two electron domains, yeah, go ahead.
Okay, so on the last, not the last slide. We had two.
This one?
For the
This one?
ethylene. For the ethylene.
Oh,
We had three.
yes.
So why did we have three?
There it is, right? This one?
Yeah.
We have three here because there's an electron domain here,
Two.
here, and then here.
Yeah. So why would it the triple bond be a domain?
The triple bond is a single domain, right? So when you go to acetylene,
No, I know, because with the
which notice though that in ethylene there was an extra hydrogen right there, right? That's why it had three electron domains. It had that one there, that extra hydrogen there had an electron domain, and then that one there, right? So that's three. But here we only have a single hydrogen. There's only one bond here to hydrogen. That's one electron domain. And then there's only one bond here to carbon.
Oh, it's not repeating. Oh, okay, I get it.
Yeah. Okay.
So you only count one hydrogen carbon bond.
Domain. Don't say bond.
The domain.
Yes.
Sorry, domain.
One domain here, one domain here.
Okay, thank you.
Yeah, no problem. So when you look at acetylene, then it only has two electron domains, right? So what do you think its hybridization going to be? If four electron domains gives you sp3, exactly, right? You get sp because only one s orbital and one p orbital will hybridize in order to give you the two electron domains, right? So here we have the same picture we had before. Now the 2s orbital hybridizes with one of the electron orbitals, one of the electrons of the 2p orbitals, and now you have two degenerate sp orbitals right there, right? So two electron domains means sp. Go ahead.
So when it looks, it says if the steric number is 2, then it is SP. So that's something as domain.
Exactly. I haven't gotten that far yet, but yes, that's exactly right. Yes, the steric number is the same thing as number of domains. I just don't like using the word steric number because it doesn't explain what you're actually counting, you know? But I'll tell you, we'll talk about it more in a second. So notice then, right, then that we have sp orbitals here, right? So what's going to happen then? One of these s orbitals here, these sp orbitals, the s orbital, right, will form the hydrogen-carbon bond, right? The other one of these hybridized orbitals will form one bond between the carbon and carbon, right? And then the other two bonds are going to do what? Where do they come from? They come from the two p electrons that are not hybridized, right? Because remember, green is not hybridized; they're still p orbitals, right? So the thing to know then, the take-home message here then is what? A triple bond consists of what? One sigma bond, which I forgot what the symbol for sigma is for some reason. Oh, like that. Yeah. And then it has, not two, three, yes, two. It has two pi bonds. Okay? A triple bond consists of what? One sigma bond and two pi bonds. Why is that? Because one of the sigma bonds comes from one of the sp orbitals, right? And then the two pi bonds come from what? The two unhybridized p orbitals. Because p orbitals make what? Pi bonds. And now that's how you get a triple bond. Does that make sense? It's crazy stuff. And of course, I jumped the gun again because here's a picture of that. So here, notice, right? Here's the sp orbital here between this hydrogen and this carbon right here. And then there's the sp orbital there between these two carbons here, and they form what? A sigma bond, right? Make sense? And then here's one pi bond here for one of the two p orbitals, and then here's the other pi bond for the other two p orbital, right? It's good stuff. All right, this is going to be the last. Oh, go ahead. Yeah. Yes, that's what a triple bond consists of. Yes. One hybridized, you have one electron from the sp orbital, the hybridized sp orbital, right? The two s orbitals gone now. So one of these here forms a sigma bond between the hydrogen and carbon. One of these electrons here forms a sigma bond between the carbon and the carbon, right? So that's one bond of the triple bond. And then you still have two p's up here, two p electrons up here that are not hybridized. See, notice they're the same energy still, right? And p electrons do what? What do they form? Pi bonds, right? And so one p forms one pi bond, and the other p forms the other pi bond, and you get a triple bond. Does that make sense?
Yeah, I have one more question.
Sure, go ahead.
Um,
I know it's riveting stuff, isn't it?
so you said that. What did you say? Sorry, I just want to write it down. About it's whatever bonds to a single carbon or something.
Whatever
It's
bond.
like okay, so like on ethylene, right?
Oh, yeah. It's however many electron domains is to a single carbon.
Okay, so like, sorry, I just want to make sure I have this right. So ethylene, right?
Mhm.
It had like one going. It had two hydrogens going to the same carbon, like how it was written. It
Yes.
was like C H
Yes.
H.
Yes.
So we counted that as two, though.
We did because there's two separate bonds there, two separate domains. So I want you to answer this question then. Luckily, the lab that we're doing today is perfectly attuned with the end of this lecture because you won't be able to do this lab without this lecture. So go ahead and answer this question then. We were just talking about the sp orbitals, right? What is the character of each of an sp hybridized orbital? Yes, 2 electron domains. That is correct. I forget how to talk all the time. Okay, let's see here. Where's this question at? Interference. Character, there it is. Everybody scanned it already?
Hold on, not yet.
Oh, you haven't
I
scanned?
haven't answered it.
Oh, I'm just saying, have you scanned it? If you scanned it, I can switch it over.
Hold on.
I'm holding on.
Sorry.
Oh, this is perfect. This is perfect. Still only have 9 responses. 10 responses. One more. Still waiting for one response. There we go. Oh, I love this. This is perfect. Finally, I can do this. Yes, you're going to need to discuss. Because quite literally, everybody answered something different. So, everybody answered something different. So, I want you to get with your houses and talk about this. Get with your house and talk about this. And then we'll vote again. Think about this. I'm talking about you guys. I'm a Hufflepuff.
We both chose 50-50.
I can't tell you what I would chose because I know the answer. So,
Well, the reason we chose that is because, like, well, my logic was whenever it was SP2,
yeah,
it was 33 and 67,
yeah,
and then you took away a P, so then it goes 50-50. And then for like SP3, it was 25 and 75. So
that's beautiful logic.
okay.
Is that what you think too? You sure?
Yeah, she's smart. She knows all the answers.
I'm sure.
She gets them all right.
I know it's always the quiet people you got to look out
Yeah.
for. See, loud people like me, we have no idea what we're talking about.
Yeah, she's quiet and she knows all the answers. I'm like, speak up.
I'm literally like making this stuff up as I go along. So, are you worried? All right. I'm going to clear this and give you guys a second chance. Okay? Huh? Don't scan it yet. I got to clear it first. I'm going to pretend that you guys didn't answer everything wrong. So, or everything differently, rather, is what I meant. Okay. Scan it again. Try again. I mean, maybe there's a typo in my question. Maybe that's why people are answering all differently. Okay, we've only got 5 responses. No, take your time. I'm just giving you an update on responses. Let me give you a hint. There's always patterns in chemistry. Okay? There's patterns in periodic tables. There's patterns in S character and P character. There's patterns everywhere. That's how we figure out chemistry, by observing patterns. So look at what you have ahead of you. Oh, sorry. Look at what we've already talked about, right? And see if you can extend the pattern to this question. There is a specific reason why I didn't tell you what the P and S character is. There is a specific reason why I didn't tell you what the S and P character is for this bond.
I see exactly what you're saying.
Okay, everybody responded? Okay, let's look and see what everybody said. All right. The answer here is 50-50. And most of you got it right. I'm very glad about that. And it makes sense, right? Because when you had SP3, it was 25-75. When you had SP2, it was 33-67. So now you have one half of it is what? S. The other half of it is P. So it's 50-50. Okay, everybody get the, sorry, go ahead. No, not specifically that way, no. I won't make anything like that looks complicated like that. Yeah, and it's because you can't hold it in your hand and see it is why. Okay, so good job there, everybody. I'm glad that the putting you in houses didn't wasn't in vain. So here's some things that you need to specifically know about the strengths. When I write them out like this for you to see, right, and I don't just talk about them, it means you need to know it, right? Which should be stronger, a pi bond or a sigma bond, right? Well, a sigma bond is considered stronger as it requires almost twice the bond energy of a pi bond to break, which makes sense, right? Huh? Yes, the sphere one, right? Two spheres coming together to make the sigma bond, right? So that's obviously stronger. It takes twice the amount of energy to break that bond than a pi bond, right? And then the other question is, which should be longer? As an sp3 sigma bond overlap, or an sp sigma bond overlap? Yeah, so sp3 bond lengths are the longest, right? Because remember, as you get single bonds are the longest bonds, right? And the more bonds you get, the shorter it gets. Remember? Single bonds are the longest, double bonds are in the middle, and then triple bonds are what? The shortest. So to have an sp3 orbital, right? They're single bonds, aren't they? Right? sp3 orbitals, remember methane? Methane has 4 hydrogens, all of them single bonded. Go ahead.
So SP2 is a triple bond. SP2 is always a triple bond.
No, not necessarily. Remember that
Oh, you're counting domain.
we're counting domains, number one, but a triple bond is consisted of 2 pi bonds and an sigma bond, right? So that sigma bond is what's made of the 2 sp orbitals, right? But the other 2 are made of pi bonds
Okay.
in the triple bond.
So the sp3 bond, there's 2 single bonds. I mean.
Yes, correct. An sp3 orbital is a single electron and a single electron making a single bond.
Okay.
Right? Whereas when you have an sp2, right? What is that? That's going to be the one that has a double bond and 2 hydrogens off of it. Yeah. Right? So that's important to know. Okay? But equally important to know is what I already said before, right? Here is a single sp3 hybridized bond, right? Carbon, carbon, with 4 things attached to it, right? So what's in between? A sigma bond. That is an sp3 hybridized carbon. And look at its bond length. It's 1.54 angstroms, right? Then we have an sp2 hybridized carbon. Its bond length is what? 1.34. Just remember, I know I keep on harping on this, right? This right here is literally an sp3 hybridized bond. Whereas this here is one sp2 hybridized bond, right? Making a sigma bond, and then one what? One pi bond, right? Remember that, okay? And then when you have a triple bond, it's got the shortest. One sigma bond and what? Two pi bonds, right? And it makes sense. The more bonds you have, the closer it gets to each other, right? The more strength it has to hold it together, right? And the bond energy corresponds to that. A single bond only takes what? 348 kilojoules per mole. A double bond takes 632 kilojoules per mole. And a triple bond takes 820 kilojoules per mole. You want to be getting skin cancer if you did have that in your DNA, right? The problem is you have this in your DNA. And that's why you get skin cancer, because UV light corresponds to the very similar bond energies, right? It's crazy stuff. So Oceana actually came up with this earlier today. She jumped the gun and told me about steric numbers. But I wasn't ready to talk about that yet. But that's okay. So notice, right? We have this theory called valence shell electron pair repulsion theory, right? And what it says is that valence electrons will repel each other. Okay, valence electrons will repel each other. It kind of makes sense because valence electrons are all negative, and negative things, repel each other. You put two magnets together that are both negative on one side, and they'll do what? They'll repel against each other. In fact, a lot of physicists consider electrons little tiny magnets, right? And they're pointed upwards or pointed downwards, just like magnets can be pointed, right? So when we were talking about before electron domains, and we're talking about before electron, the amount of things connected to the carbon, right? That all corresponds to the steric number, okay? That's the steric number, okay? So if you saw here, we have our methane here, right? It has a steric number of 4 because it has 4 bonds, electron domains attached to it, right? So really what it is that it's the number of sigma bonds, right? Plus the number of lone pairs. Carbon has no lone pairs, has 4 sigma bonds or 4 electron domains. What's its steric number? It's 4, right? Let's look at ammonia here. So the reason why Hannah, I couldn't just say that you could count the electron domains by saying it's the number of things that are bonded to it is because electron domains includes lone pairs. And there's nothing actually connected to that, right? So when you look at this, here, ammonia has 3 hydrogens connected to it and a lone pair. So it has 4 electron domains. What's wrong? Oh, don't worry. Let Gibbs energy field deal with that. Gibbs free energy is the energy that things inherently have, right? And so if you leave something long enough, eventually it'll just evaporate. So whenever I spill water, I always say, "Oh, just let Gibbs free energy deal with that," because it'll dry eventually. Because because molecules, especially water, right, they all have energy that they're bouncing around, right? That's why water flows the way it does. And some of them sometimes will get just enough energy that they will evaporate, right? They'll get high enough energy that they'll evaporate. You can make them all get there really fast by heating them up to 100 degrees Celsius, but while they're sitting at room temperature, only a couple will get enough energy as they're bouncing around with all this momentum, enough energy to actually evaporate, right? And so if you leave a bottle of water, not a bottle, like a bottle of water long enough, all of them will get enough energy to evaporate, and that's Gibbs free energy, if you were wondering.
Okay,
So yeah,
for this, you're saying that
tangential.
the
Sorry.
reason why we couldn't
It's okay, Michelle.
count
The reason why, remember earlier I said the reason why I said you couldn't, I said you could for a moment there, said you could count the number of things bonded to it and say that was a number of electron domains, but that really isn't true, because if you look at nitrogen, right, it only has 3 things bonded to it, but it also has a pair of electrons too, and it has 4 electron domains, giving it a steric number of 4, right? 3 sigma bonds, 1 lone pair, steric number of 4.
and which one is the lone pair?
The lone pair is the one that doesn't have a bond to it. It's a pair of electrons right here that doesn't have a bond to it.
Oh, okay.
Yeah, lone pair of electrons, right?
So
So electrons are either bonding electrons.
I see what you're saying.
Yeah, electrons are either bonding electrons or they're lone pairs. Okay. So again, look at water here, right? Water has 2 lone pairs and 2 bonds, right? And what do you have? Steric number of 4, 4 electron domains. All 3 of these are what hybridization. This carbon, this nitrogen, and this oxygen, what are the hybridization? Huh? SP3, yes. They're all SP3. Yes, because all of them have the same steric number, 4. Remember, electron domain is the same thing as steric number, right? So here, 4, 1 here for the lone pair, 2 for this bond, 2 for this, 3 for this bond, 4 for that bond. Here, 1 electron domain, 2 electron domains, 3, 4, right? Steric number is 4, okay? So the steric number is also known as the number of electron domains, and it can instantly tell you what the hybridization is of the central atom, right? So let me ask you this. What if you had a steric number of 3? What is your hybridization? Yes, exactly. And what if you had a steric number of 2? SP. See, you're getting this. This is good. It's good stuff. Good stuff. Okay, now this is what takes us. Oh, we just skipped ahead, right? So this is already written for you in the notes. We skipped ahead. Steric number 4 is sp3. Steric number 3 is sp2. Steric number 2 is sp. The only thing you have to remember from here is that steric number is the exact same thing as number of electron domains. Okay? And electron domains includes bonds, area where there are bonds, and areas where there are lone pairs. Okay? Okay. That takes us to our lab today. Our lab today is called the VSEPR lab because it's talking about how different atoms are spaced in space to each other because their valence electrons are actually repelling each other, right? So remember before, if you have an sp3 hybridized atom, like a carbon, you have 4 valence electron pairs, and you form a tetrahedral. So know this, sp3s always form a tetrahedral. And the prime example, right, of an sp3 is methane here with this carbon in the center, right? This carbon is sp3 hybridized, and it has these sp3 hybridized orbitals making sp3, and since it has 109 degrees, 0.5 degrees all the way around between these hydrogens, that makes it a tetrahedral molecule, right? Quite literally, a tetrahedral shape, if you didn't know, is a 4-sided shape that's not a square or a rectangle, right? Okay. Excuse me. Turns out that these other ones too that we were just talking about before, ammonia, it's also a tetrahedral, right? Because over here we have the hydrogen from the ammonia pointing downwards. We have the hydrogen from over here pointing downwards, and then we have the hydrogen over here pointing downwards. And the reason why they're pointing downwards that way is because nitrogen has a lone pair that's not being bonded to anything, right? Remember when you look at the periodic table, right? It has how many valence electrons? 5, but only 3 of them are bonding, right? 2 of them are in what? A lone pair. So these guys here, they're repelling, they're literally repelling the electrons that are bonded to this hydrogen, making them point downwards, making a tetrahedral shape. Okay? sp3 as well. Same thing here, right? This is sp3, 1 electron domain there, 1 electron domain there, 1 electron domain here, and 1 electron domain here. Again, these are repelling these down, giving it this 105 degrees bond angle. And what do you have? A tetrahedral shape. So know that sp3s always do what? Tetrahedral shapes. Okay. So let's look at some common ones. Okay. Some common ones. The molecular geometry is described for atoms only that are bonded to a central atom, but then electron group geometry includes lone pairs. Okay. So, for example, we have methane here. Okay. 4 bonding pairs of electrons, 0 lone pairs, has a steric number of 4. This is a good chart for you to memorize, by the way. It's tetrahedral, right? Because it's short, number 1. right? And it actually describes a lot of good examples. You should thank me for this chart. I made this chart. You're welcome. You're welcome. It's like that. It's like the Rock in that movie Moana. You're welcome. you know. Um, you're welcome for saving your lives or something. Anyway. Okay, so it's tetrahedral here, right? For the predicted molecular geometry. Okay. Well, all three of these are here tetrahedral. Sorry, both of these are tetrahedral, right? For the electron uh, predicted arrangement of electron pairs and then predicted molecular geometry or tetrahedral for methane. But then when you look at ammonia here, right, it actually had 3 bonding electrons, 1 lone pair, still had a steric number of 4, right? It is still also tetrahedral, right? But interestingly though, it is called a trigonal bipyramidal. Why is that? Let's go back real quick and look. If you were to draw a shape here, from here to here to here, right, and put a base at the bottom, what do you get? A 3-sided pyramid, right? Crazy stuff. Okay, let's look at water. Let's look at water. It had 2 bonding electrons, 2 non-pair, no, yeah, 2 bonding electrons, 2 lone pairs, still a steric number of 4, still tetrahedral, right? Because with the lone pairs in there, it's tetrahedral. But when you look at the water molecule by itself without the electrons, right? Without the lone pairs, like just pretend the red stuff is gone, what do you have? Just a bent molecule, right? A V shape. Okay? Then we have boron trifluoride, right? Boron trifluoride right here. It's trigonal planar on both because when you draw a boron trifluoride out, it's actually flat. It looks like this. It should be a little bit better than that. Let me draw that again. There we go. Right? So it's literally flat. That's what it looks like. That's what boron trifluoride looks like. It's flat. So that means, so a smart word for flat is what? Planar, right? Like how I've been doing a lot of woodworking lately. Like I built a deck during the pandemic when we were all stuck at home, and I had to get a planer. This thing called a planer, and literally what it does is that when you buy wood from Home Depot, it's not flat. It's like all kinds of warped and bent all over the place. So you stick the wood into a planer, and it makes it flat, right? So that's why this is called a trigonal planar, right? Because when you look at boron trifluoride, it's flat. Literally, it's flat, right? Trigonal planar. And then the last one, beryllium hydride, right? Right here, right? It's linear because it literally looks like this. It's not bent. It's not 3-dimensional. It just looks like this, right? That's beryllium hydride, and it's linear. 2 bonding pairs, right? Steric number is 2, so it's linear. Okay? Yes, ma'am. Oh, sorry, one more time.
The difference between the trigonometric pyramid and the planar is that
Yeah, one is a.
had the lone pairs holding it up.
It could be, or it could be an atom up there. Yeah, it could be, or it could be an atom up there. Yeah, it could either be a lone pair making a little point at the top, or it could be an atom too. One or the other. Depends on the molecule. Okay. So these are all sp3, right? And just showing you one more time the importance of lone pairs, right? These lone pairs here make it all tetrahedral, right? But when you take those lone pairs out to make the predicted shape without the electron lone pairs, then that becomes a trigonal pyramid, and that becomes a vent, right? But since methane didn't have any lone pairs, it's the same shape both ways, right? They're both tetrahedral. Oh, dang it. I jumped the gun again. So here's boron trifluoride. I had to draw it for you, but I didn't have to. It's right here. Boron trifluoride is an sp3. Why is it sp3? Because it has how many electron domains? 1, 2, 3, right? Okay. So sorry, sp2. I'm so sorry. I'm already confusing you, and I'm making it worse by saying it wrong just now. So sorry. Trigger. I'm gonna have to scratch that out in the video. um, sorry, boron trifluoride, right? Is sp2. Why is it sp through? Sp2. It's got 1, 2, 3 electron domains. They're flat, and so it's 120 degrees all the way through, right? Which is actually the measurement angle measurement of a triangle, an equilateral triangle. And so this is what it looks like right here, right? There's boron in the center, sp2 hybridized right there, sp2 hybridized there, sp2 hybridized there. Trigonoplanar, right? And you notice there, Naraya, that there's no lone pair at the top, and that's why it's flat, right? Whew, okay. Yeah, see, this next slide literally says what you were asking right here, right? Realize that the boron atom and boron trifluoride is sp2 hybridized. There are 3 bonds made of sp2 orbitals, and the unhybridized p orbital is empty, means no electrons in that p orbital. That's why it doesn't have a. That's why it's not trigonoplanar. Okay, next we have sp, and I talked about this already in the slide before, but I guess I'll talk about it again, right? Sp. Beryllium here, right, has 2 electron domains. That's why it's sp, steric number 2. And what is its shape? It's linear, right? Bent is probably the easiest. So, you're welcome, right? Because I made this chart for you here, right, that tells you exactly what is what. See, steric number 4, sp3, it's tetrahedral. How many lone pairs? None? Then it's a tetrahedral. How many lone pairs? If there's 1 lone pair, trigonal pyramidal, right? So that's like the ammonia. And then 2 lone pairs, bent. See? Or over here, sp2, steric number 3, sp2, right? It's going to be trigonoplanar. If it has 1 lone pair, it's bent. No lone pairs, it's trigonoplanar, right? And then steric number 2, sp, hybridization, linear, right? It's linear, and it's linear. That's it. You're welcome. This slide here literally is a chart, right, that will answer every single question about hybridization. As long as you know how to count what? Steric numbers and number of lone pairs, right? Okay? You're welcome. All right, last question before we actually get started on lab today. And this lab should go pretty fast, honestly. Again, with this question, remember the patterns. Remember the patterns. If you have to use a little chart, you can. What number is that one? There it is. Remember the patterns. Everything is a pattern. I feel like you guys have more energy now that we've.
I ate, yeah.
Even you seem like you have. I'm totally kidding.
I'm really not trying to be rich whenever I say this completely honestly. But my roommate recently going out with her car.
Uh-huh.
She's at work right now.
Okay.
You said the lab was going to get done early.
It is going to get done early.
Do you think it'll get done by
what time?
3?
Oh yeah. Oh yeah.
By 3?
Yeah, I'll get done by 3. Oh yeah. It will definitely be done by 3. I'm kicking you out if it doesn't get done by 3. All right, let's see what everybody answered. Oh, okay. Sorry. 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 All I can say is remember the patterns. Chemistry always has patterns, right? When you get into the higher chemistries, there'll be like, that's a really cool skin on your MacBook.
Thank you.
Oh, it's a cover. Mine's red though. What was I saying? Dang, I lost my train of thought. Oh, yes. Remember the patterns in chemistry. When you get into the higher chemistry, so there will always be exceptions, but the patterns really stay true, like in Gen Chem. 9 people so far. 10 people so far. 11 people. I am so proud of all of you. You have no idea. Because you remember the pattern, right? Because this is silicone tetrahydride, right? Silicone is in the exact same group as what? Carbon, right? Carbon is what when it has 4 bonds to it? Tetrahedral. So what does silicone have when it has 4 bonds to it? Tetrahedral.
I guess B because I saw H4.
You what?
I saw H4.
Yeah, that's why I guessed it.
I was thinking tetro, whatever it is.
That works too. Whatever makes you happy. But the answer is always either on the periodic table, right? Or that little chart I gave you. You're welcome. Okay. so so all right. I don't even have to make you guys talk about it. Okay, so wow, I can't believe we actually got through an entire lecture today. That's crazy.
We can end live at 2:20.
Right? Wait, what time is it? Okay. No. Okay, so we'll have a Blackboard assignment that I'll post today. It won't be due till Monday, and then we'll have a quiz in your section on Monday. Yes, the one that I posted last Monday on Labor Day. Yeah, so what happened was, I had a Labor Day weekend just like you did. And so I didn't post it till Monday, and it's supposed to be due like today, but since I missed it by 2 days, I gave it to Friday to do it.
Okay, another thing. You said you were gonna give us all points back.
I haven't done that yet. I'm still going through grading a bunch of stuff right now. Okay. So, does everybody have their lab? Let's work on your lab now.